So here is part 4 of the Pythagorean Theorem lab proof, where once you've actually done parts 1 to 3 and you've played around with the given provided squares, the given provided triangles, we'll now answer some follow-up questions that will lead us to discovering that Pythagorean theorem equation. So the first two questions, we have question 11 and 12. We have question 11, where it asks, how is the area of the printed square on page 1 related to the area of the printed square on page 2? So you should be looking at those printed squares on those 2 pages when we go through this question, and then explain how we reached that conclusion. And then question 12 is then asking, how are the 4 right triangles that you cut out at the beginning of this lab related to each other? So you should have those 4 triangles, you should be looking at them as well, and then we can explain how we reached the conclusion for the relationship that they have. So the printed square on page 1 and the printed square on page 2, here we have those 2 printed squares after we've placed and found the patterns for the other squares and triangles on them, but you should come to the conclusion that the original printed squares are congruent. So both of the squares have a side length that is equal to the sum of the legs of the triangles. We have this side length of A plus this side length of B from the triangle. And in the other square, we also have the side length of A from the triangle. And then if we move and think this is the same as the side length of B from the triangle. So if the 2 squares have the same side length, they're going to have the same area because area is equal to the side squared. And if they have the same side, they're going to have that same area. So the area of the 2 squares is the original squares are congruent, so now their areas are going to be equal. So now, how are the 4 right triangles that you cut out at the beginning of this lab related to each other? Well, those 4 triangles are congruent. If you see, we have all 4 of the right triangles here, and they all have legs that are B units long and A units high. Also, you could stack all of the right triangles on top of each other, and they all are the same exact triangle. So all 4 triangles are congruent. Now we'll move on to the next question, 13 and 14. Question 13 is asking, how are the areas that you found in question 6 and question 10 related to each other? And then how we came to that conclusion. And then question 14 is asking if we can write an equation that represents the relationship we're finding in question 13. Well, the areas that we found in question 6 and question 10 are equal. So we have and we know that the areas of the 4 triangles are equal, and the original printed squares are congruent. We just said that from the previous follow-up question. So we know that since the printed squares are congruent, that the areas are equal. So therefore, if the 4 triangles occupy the same area, then the remaining areas, or the area for the square parts, are equal. So for example, the first printed square, we know that the area we found in question 6 was C squared. And then the areas from question 10 were A squared and B squared. So we know that those are going to be equal amounts of area, because if the 4 triangle, here we have triangle 1, 2, 3, and 4 occupying the other parts of that square, and we also have in the other printed square triangles 1, 2, 3, 4 occupying the same amount of area, then the remaining area has to be equal to each other. And this directly leads into the question 14 for the equation we can write, is the area from that big square, C squared, is equal to the sum of the area from the 2 smaller squared. So C squared equals A squared plus B squared. And right there you can see that's the Pythagorean theorem. We have C squared equals A squared plus B squared. Now another way to see the Pythagorean theorem is now to complete part 5 with these follow-up questions. So we're going to go through the answers for question 15, 16, and 17. where we're first starting off with question 15, where it says, what algebraic expression represents the side length of the printed squares, and how would we reach that conclusion? So we have the two printed squares, and we have the side lengths are going to be equal to the sum of the legs of the triangles. So here we have A and B, so that would be the expression A plus B. Even if you use the other square, which we know is congruent to that first square, you would still have that side length of A plus the side length of B. So that is the expression for the side length, right? When the triangles are placed next to one another, they fit inside the printed square when the measurement of the short leg A and the measurement of the long leg B are next to each other or adjacent. Now, the expression you get when you multiply the side lengths together, well, you would have A plus B times A plus B. That's finding the area of the square. And when we simplify that expression from A plus B times A plus B from question 15 and technically question 16, by using the distributive property twice and combining like terms, you get the product of A squared plus 2AB plus B squared. Again, if we distribute A times A is A squared, A times B is AB, B times A is also AB, and B times B is B squared. And then you can combine your like terms to get A squared plus 2AB plus B squared. And again, this is a little bit advanced algebra. This is working and multiplying what are called binomials, which you'll learn in the future. But what's most important is to know that our expression for the area, A plus B times A plus B, simplifies to A squared plus 2AB plus B squared. Then we now have questions finally 18 and 19. So question 18 says, using the arrangement of the shapes from question 5, write an algebraic expression to represent the area of the entire figure. So let's go back and look at our arrangement from question 5. So the area we first found earlier in the lab, the area for just that square in the middle, we had C times C was C squared. So that's part of the area. That would be C squared. But now we want the area for the entire figure, so that's going to include the area of the 1, 2, 3, 4 triangles. Now thinking of our formula for the area of a triangle, that would be 1/2 base times height, which we know all 4 triangles have a base times height of AB. So to find the area, we would start with that C squared for the middle square, but then you would have 4 to represent the 4 triangles. There's 1, 2, 3, 4 of 1/2 times A times B. Right there, that's the area for the 4 triangles, and then we're multiplying by 4. We can then simplify a little bit by multiplying 4 times 1/2 to get the area is going to be C squared plus 2AB. That's representing, again, remember, that's representing the area for that whole entire rectangle. But we already found an expression for the whole entire rectangle. Let's remember, we just said it would be A squared plus 2AB plus B squared. Remember, that's if we use the side length of the square to find the area. So what we can do is we can now set those expressions equal to each other. We can set A squared plus 2AB plus B squared equal to C squared plus 2AB. And if we simplify this equation by subtracting 2AB from both sides, we end up with A squared plus B squared equals C squared. We get the Pythagorean theorem again. So working through these follow-up questions, you can see where the Pythagorean theorem comes from, where it's developed, and how it was discovered by mathematicians, including Pythagoras himself. It's a proof of why that equation holds true all the time for right triangles using these properties of squares and the relationship between area.